Okay, introduce Paul Washington. You want to introduce yourself, Paul?
Yeah, I'm a geologist. I started off life as a history major. Basically finished that and then said, "Nah, geology's caught my interest," so I became a geologist.
Okay,
I've
that the
spent my
screen
life
is a little,
mostly doing that.
we can't see the details on your screen. It's a little bit too small.
I can I can make it out, but yeah,
Okay,
there's a
all
zoom
right.
function.
I moved it to my bigger screen so I can see better. Then go ahead.
Okay, and so what I'm going to do, I'm going to discuss the very basics of what was going on last time, not getting into all the different types of materials, but rather talking about the basic mechanics because I'm a mechanics
What,
person and a
Paul,
history person.
Paul, what do you mean by last time?
Your last meeting,
Oh yeah, okay, our
your
last
last
meeting on a very, very similar subject. Okay, and so he's
right.
talking about the various technologies that could be used to brighten clouds. Okay, go ahead.
Okay, so basically, when we look at the atmosphere and we look at what we can do with the atmosphere to dim the sunlight coming in, the input, we're talking about aerosols and uh, cloud albedo. And cloud albedo is increasing anyway because you've got more and more moisture in the atmosphere, so the clouds are denser. That's just the function of global warming. Um, and in fact, the amount of increase is probably about the same as increase that you can get from, let's say, throwing salt into the clouds is about the equivalent of what you can get from a 1 degree of solar of global warming. That is 1 degree warmer, 1 degree C warmer ocean surface. Every degree of ocean surface increases moisture levels in the overlying atmosphere by 7% approximately. So we've got, as we warm up the oceans, we're going to have more. The problem with throwing salt is how to get it up there into the troposphere so that it actually does something. You've got about a kilometer that you've got to overcome before it gets sucked into the clouds, or shall we say, before it's part of the clouds. The clouds are basically in that zone from about a kilometer up to about 10. Actually, in Louisiana, it gets up to about 12. By the time you get to the equator, it can get up to as high as 20. No, up to as high as 20, not usually quite that high. Um, and the stratosphere is above that, and that's where the aerosols you're mainly looking at. The aerosols are usually in the that we're talking about are in the lower end of the stratosphere. Volcanoes just don't kick anything more than about 80,000 plus feet. In other words, 25 to 30 kilometers up. There 30 kilometers that you almost never get anything that high. So you're talking about the lower end of the stratosphere for aerosols, and you're talking about having to get things up into the above the boundary layer, above the bottom kilometer, and that's the crux of the problem for dealing with salt. But there's also the problem that when you toss salt into a water-based system, it's going to dissolve. So you might as well just shoot it as water spray rather than as try to extract salt and inject it. It's going to be salt water in the end anyway. And then the question is, what what is the usefulness of that? Well, it actually will suck in a little bit more water from the surrounding atmosphere. What have you done? You've added a little bit more to the clouds. They're going to rain faster or sooner. that's essentially what you're doing. So how much do you gain? Probably not a hell of a lot. So let's go on and rather than talk about, yeah, there are all sorts of different types of aerosols, and sulfur dioxide, sulfur is the one that everybody is going to focus on. It's because it's the natural source. It's there, but you can get this stuff up there by plane. Planes are going at that up into the very lowest stratosphere all the time in transcontinental flights and the like. So
if you'll forgive my
approach.
interjection, if you'll forgive my interjection, it's got to be the bottom choice ecologically. Just saying.
It's not the bottom choice. There are worse choices, but it's
well,
not the top one.
Okay. Well, it's way low for me because
I come from Vermont,
sorry.
which suffered dramatically from acid rain. So I'm quite aware of that. But that's a tropospheric thing. The stratospheric, the amount of sulfur that you get into the stratosphere as aerosols is small compared to the acid of the sulfur that was in the troposphere that was causing the acid rain. So you're not really changing that balance series.
I dispute that, but I'll let you continue. I mean, look, all I'm saying is it will settle out, and I'll just leave it at that.
Yeah,
obviously it's going to settle out. It's a question of how much and how fast. So let me see if I can get this to actually advance. There we go. So, but let's look at the balance that we're really looking at. I grabbed a diagram from somebody, from actually the guy at Penn State that's teaching the class that Myron was linking to. Incoming solar radiation, only half of it gets absorbed by the surface. Something like a quarter of it gets reflected. We're trying to increase that by what, about 2%? In other words, 10% more than it's doing now at most. Probably we shouldn't even be talking about that much. And there are reasons for that. But that's what we're talking about. We're talking about increasing that reflected by aerosols and clouds proportion. And we're trying to do it in a way that doesn't seriously affect the insulation, the absorbed at the surface. No, we're going to want to cut down on the, we're trying to transfer 2% from the surface to the clouds, except that we shouldn't be doing that. Let's talk about, though, where is the solar energy actually coming in? As Myron could tell you, as a mathematician, 50% of the Earth's surface is within 30 degrees north and 30 degrees south of the equator. Within 30 degrees of the equator constitutes 50% of the Earth's surface. That 50% gets the most direct solar input. Yes, it alternates where it's happening, but that's the real, that's where probably something like 70% of all of the solar input happens. Notice what that does to the oceans. That's what stores the heat. This is actually the heat map from yesterday. So you can see the effect of the summer when it was the solar direct input was north of the equator, but it's basically there. If we can cut down on the heat coming into the center 30 north to 30 south, in other words, basically the tropics, the subtropics, we've dealt with the heat. We don't have to deal with trying to put aerosols into or whatever we do, up in the northern parts of the of North America and Eurasia, they're minor. They're minor contributors to the heat in the world. Of course, we've got the problem that if we do this, that this is always the political problem, always the political problem. It's not going to be carried on forever. And if we don't do something about the CO2 problem, we're going to be facing this temperature bump at a later point, and we're going to have to do increasing geoengineering to keep it from bouncing back. And at some point or other, people are going to decide that it's not worth it. The problem that I have, one of the big problems that I have politically is watching politics over the years. If you come up with a solution that partially solves a problem or appears to solve a problem, nobody's going to work on the other part of it that actually solves the root cause. If you put a Band-Aid onto the cut, they're not going to come back and look at the root cause. They're going to let that be and let the wound continue to fester. So that is my biggest problem with this geoengineering thing. You've got to solve the root cause. Or I should say that's one of my big problems.
If you read, I think you probably read at least the opening part of my paper, right? And I state right up front, you've got to both be removing carbon and stop adding to the problem.
Well,
Richard,
given the way that the world, the natural system works, it takes carbon out of the atmosphere fairly efficiently if we can stop putting it in. It will revert, but we got to stop putting it in.
Yes, but the problem that I would like to point out as, by the way, a very long time now earth science researcher with credentials you haven't heard. I've spent 7 years leading a large team at UC Berkeley, blah, blah, blah. But just to get right to the point here is that the temporality of the problem is the biggest part of the problem. Simply put, we can't only rely on the natural systems to do their thing. Yes, they will help, but if we are to prevent other cataclysmic elements of which I'm aware and few are, namely that while it gets short shrift, we have a very serious risk of what I'll call global flooding. Okay, it's not genuinely global flooding, but it is massive sea level rise that doesn't come inches a century. It comes 10 and 20 meters at a time when it does in the geologic record, and I know a hell of a lot about it, and all I'm saying is we have to prevent that, and we're not going to prevent it if we're allowing the soil uptake and the tree growth and all to be the only way we're getting rid of the damn carbon. Just saying. I'll leave it at that.
The evidence for that for that rapid sea level rise, or shall we say, not the rapid sea level rise, but the mega sea level rises of the early Holocene.
That's not mega. Oh no. We're 186 feet roughly from the highest sea level that's known in geologic history.
I am quite aware of that because I lived at 186 feet above sea level in Louisiana.
There you go. Okay. All right. Wait, Louisiana?
Richard,
okay.
Please stop interrupting.
Yes,
Paul.
I taught at ULM for a dozen years.
Okay. Let Paul talk, and then you chime in later, Richard, please.
Okay.
Sure.
So, but my real problem has to do with the effects of reducing solar input is on the global population. and I mean on the population specifically, because close to 50% of the global population lives in or very close to in water stressed regions, or I should say, yeah, water stressed regions. If you cut down on the solar input, you cut down on the amount of water available, because the solar input is the thing that's driving evaporation. If you cut down on the solar, the seawater temperature, you cut down on the evaporation, you cause lower rainfall. And this is what has been shown several times, both naturally and anthropogenically. And that's where I really want to go with this. What is the problem with cutting down on solar input? First of all, there are two aspects to it. Let's first of all look at the spectral irradiance. The visible light range is the highest amount of input proportionately. It's also the level, the light that is creating photosynthesis. That's the same wavelengths that we're seeing are what are in photosynthesis. Actually, it's slightly larger, but it's effectively the same.
Right, a question for you, Paul. What do you mean by outside temperature? That's the temperature of what altitude?
Outside atmosphere. That's outside. That's the space spectrum coming out of the sun.
So when you see it
And
from 5,000 feet out, that's what you see?
So if you get outside, if you were to get outside the atmosphere, that's what you'd be measuring. Then what gets down to sea level, in other words, after absorption and reflection and all that, is the darker level inside.
I see.
If we cut down on the amount of light coming in, we're cutting down on the amount of photosynthesis possible, which is cutting down on the amount of food we can produce. We're also cutting down on the water that we can put into the system. These are not good things to be playing with. So let's talk about some case studies. The natural ones are the ones that everybody likes to go to. Tambora, 210 years ago, huge volcanic eruption, something like several times the size of Pinatubo, in Indonesia, kicked a huge amount of sulfur dioxide into the stratosphere, and there were 2 years of real cooling. It was late enough in the year. The next summer, 1816, is known as the year without a summer. We had killing frosts and snow in Vermont at low altitudes right through July. There was icing on rivers in Pennsylvania in July. That's how much that was. Now, how much of an effect did it have? It lowered solar input by about 2%. That's what 2% does. That's a huge effect for 2%. Now, true, we were in the later ends of the Little Ice Age, and it probably hit at one of the lower cycles there on top of it, but it caused global catastrophe, global all across Eurasia and actually into India as well. You had crop failures, North America crop failures, so that you had the winter of 1816-17 was global famine. In London that winter, the price of bread. Now think about it. London was the center of the economic universe at the time. It was the center of a global scale empire. So it could get anything it needed. London, the price of bread went to $1 sterling per pound, per loaf. In other words, it became as valuable as silver. Pinatubo in 91. I remember Pinatubo. It happened late spring or June-ish, late May, June, something like that. I was getting ready. I was working in North Carolina for the state, and I was going to be doing field work out outside for much of that summer in the southeastern corner of the state. And I was not looking forward to it. I'm a Yankee. Southern summers I find too hot. North Carolina, it was only going to be like 92 every day. When I got to Louisiana, I found that it was 95 every damn day in the summer. Okay. I was not looking forward to it. Pinatubo happened. It turned 92 every day into 88 every day. Now, the actual effect of Pinatubo was less than a degree for the globally. Locally there, it was about 2 degrees C. Globally, it was less. So, but it made that summer a lot more pleasant for me. But let's now look at anthropogenic things. I want to talk about Indian industrialization versus East Africa, the Middle East, and Central Asia. And then I want to talk about China's industrialization and the Western US drought. And then I'll talk about America's effect on the USSR and the New York City water shortages of the 1960s. This is a picture of actual smog transport off of the Indian Peninsula over the Arabian Sea. Now, that's a lot more than we usually are talking about in terms of pollution coming off of land and onto the water. But that is an illustration of just how significant the pollution coming off of India is. There is a strong linkage between the industrialization of India over the last 40 years, 50 years, and the amount of sunlight incidents in the Middle East. It was first noticed, in fact, global dimming, the term global dimming, comes out of Israel, where you had an agricultural engineer who was measuring evaporation pans and noticed a long-term downward trend in the amount of evaporation in Israel, starting in the early 80s. And he was able to link it directly to Israel, and that
India.
India. Yeah, he was able to link it to India, and that same effect is affecting all of the Middle East and actually all of Northern Africa and all the way up in Central Asia. So if we go back to this picture, this map, we go to India and we look at where the water stressed areas are. All those water stressed areas north and west of the Arabian Sea, including the whole Arabian Peninsula.
If you'll forgive my interjection, I can't see your graphic.
Right. Okay. Think of the Arabian Peninsula.
Hold on. I'll be very, very concise, specific. Your Indian references. So when you reference Israel, you really meant India. I hope that's just a clarification.
Yes. That was a correction.
All right. Okay. But the other point here is what is the timeline again for this? Because you talked about several data points, and I'm very fascinated by those data points. So what time frame is that discovery of the data, and what is the most recent about specifically what you were talking about, please?
Well, the discovery of it was in the mid to late 80s. He realized he was seeing a consistent increasing decrease, shall we say, in a consistent
I get it.
decreasing trend in evaporation from the Israeli evaporation pan measurements.
Indian, not Israeli. Indian.
Israeli.
In that sense, he
Israel.
meant Israel. Yeah.
It was India
Okay.
is the source of the pollution that is
Okay.
that is causing the decrease in Israel.
All right, I follow you. I follow you now much better. Thank you. And any opining
also,
any
right
opining
now,
about China's
we'll get to, I'll get to that. I'll get to that. Right now,
Okay, good.
right now, Iran, which is also part of this, is sourcing its water from evaporation off of the Arabian Sea, is experiencing extreme water stress to the point that they are under water controls in Tehran. And happening to know quite a bit about Central Asia, thanks to my son marrying a woman from there. They have been experiencing increasing water stresses across all of Central Asia. That is the stands, as you would know them, of Central Asia. Yeah. They also, this is the increasing frequency of droughts in the Sahel on the southern fringe of the Sahara really picks up in that same time frame. In other words, India's industrialization is drying out a whole lot of, I was about to use a different term, but a whole lot of Africa, the Middle East, and all the way up into Central Asia. It is the sort, it's because it's putting pollution, that is reflectors, above the sea that is otherwise the evaporation pan that feeds the water for that whole region.
Did you just state, just to clarify, just that last statement you made, are you saying that they're lofting materials that are changing the albedo locally?
They're changing the albedo over the northern Indian Ocean, and that is causing the reduction in rainfall across this huge area that is already a desert to marginal desert.
I got it. Thank you. And that was a yes, but with a lot of extra data. I got it. Okay, good. Go ahead.
Yeah, it was a yes, but I wanted to make sure that I said it properly. So let's go on to China. And I'm showing a picture here of that shows 2006 data for averaged data for sulfate concentrations from China across the Pacific Ocean to the Western US. Ozone also across that same zone, black carbon across that same distance, and carbon dioxide across that same distance.
They've got,
this is the PNAS, publications at the National Academy of Sciences. They don't always put things in the best form.
Okay.
But you're talking about concentrations here that show that the pollution from China is affecting Western US. The long-term drought that the Western US, the Colorado River watershed and Western US have been in for the last 40 years or 30 some years, it can be directly correlated with the pollution levels in China.
Wow.
So,
Believable, by the way. I just want to comment for everybody else. I've been following this a little bit, and I say that's entirely believable. Please go on, Paul.
yeah, I mean, they've already said that anywhere from about a quarter to half of certain types of pollutants in the city atmospheres of the West Coast actually are derived from China. Think about that. We knew what smog was like back in the 60s in LA. They've cleaned it up, but they can't clean it up all the way because they're getting all this stuff blown in across the Pacific. That stuff coming in across the Pacific is cooling off the west of the North Pacific, and that cuts down on the rainfall in Western North America.
Forgive my interjection again, but I have personally been involved with the study of El Nino and El Nina with Victor Zlotnicki as my research partner at JPL, and we've been studying this, and I'll need to go back and confer. Do please send me an email copy of the materials you're showing now, and maybe we'll follow up in other dialogue. Thank you.
Yeah. So, I mean, this is publicly available stuff that I'm using. I'm not inventing anything new here. It's that I'm saying when you start playing with the Earth's atmosphere, that is the solar input from to the Earth, you're playing with fire here. So when we go back and we look at this, the map of the global, let's say, water stressed areas of the world, and you start thinking about changing how much rainfall they can get, cutting it down, we're talking about putting water stress problems on much of China, much of India, all of the Middle East. In fact, people have claimed that the Arab Spring was caused primarily by the reduced rainfall. Think of that as a political result. The Arab Spring actually started in Kyrgyzstan, by the way, with the second revolution. No, yeah, that was the second revolution. Was it the second one? Yeah, that was the first one, the tulip revolution that they called it there. The second one, my son had friends who were actually on the square and watching it. So this was the first one. Anyway, but you stress out an area, people can't eat or can't grow food or don't have enough water to do whatever. This causes political instability. So let's talk about North America and the Soviet Union. North America back in the 50s and 60s. Myron, you remember the North America at that time? Norm Whitriall talks about not having ever realized that snow could last as white for more than a day when he was growing up in Brooklyn in the 50s. He didn't realize it could stay white for more than a day until he actually got to grad school up in the Boston suburbs and was not downwind of major smokestacks. He thought it went through a phase change. Yeah. there was so much, and this is ultimately we found out that it was also killing the trees because of acid rain and all of that, but it was also cutting down on the rainfall in the eastern Appalachians, the northeastern Appalachians especially, and that's where the water from New York City comes from. The Catskills, the high Catskills, are totally owned by the water rights are totally owned by the city of New York. They have all of their major reservoirs up there. They pump. They've done this for 100 years. That's where they get their water. Well, they ran short of water. You know what they do as a result of running short of water in New York City? They start pumping it out of the Hudson. Not exactly, and they don't treat it that well because they don't have the treatment facilities, because they don't have to treat the water coming.
Yeah. As a native
Yeah.
New Orleanian, I would have said, good luck with that.
Yeah, well, they were pumping out of, and they actually outlawed giving out free water in restaurants in New York City in 63 and 64. Yeah, so they had a problem there. There is obviously there are fluctuations in climate in the Northeast, which always makes a problem for the Northeast. So that we've just come through a period of lowered of semi-drought here in central Pennsylvania because of the fluctuations in the climate here. But so they were obviously in one of those aggravated by this downwind of the TVA and all the other coal burning plants of the Midwest. That same pollution was being swept northeastward out over the Gulf Stream and was lowering rainfall in Western Europe, especially as you got closer, and it was causing problems for growing wheat even in Ukraine, which is why they had crop failure after crop failure after crop failure that ultimately led to the downfall of the Soviet Union. Our pollution, we put in the Clean Air Act in what, 69? And then but we didn't enforce it very well. And we finally in the 80s, we got our act together. But by that point, they were on their last legs politically, and it fell apart at the end of the 80s because of our air pollution. Just like we're having problems in California, just like we're having problems in California now because of China.
Paul, are you able to speak to what's going on with the Mississippi drying up and the rivers of Europe, the major European rivers?
Richard, please let Paul finish his spiel, okay?
Basically, that's where I'm at. That's where I'm at. I would argue very strongly against futzing around with the albedo of the atmosphere, trying to reflect more light out, because the consequences of that are actually more dire than allowing the ice sheets to continue to collapse. If we have the ice sheets, the glacial outflows from Antarctica, if they were to all collapse like they are, the ones that are on edge, we would get up somewhere between 2 and 4 meters of sea level rise.
Oh, that's wrong. Look, I have to interrupt. I'm sorry, Myron. I have to interrupt. That is so way wrong. But you've got the floor. I just happen to know.
I'm not talking about taking out the whole continent. I'm talking about the immediate first round level of sea level rise that would happen within about a 5-year period.
This still deserves a look. I'll only just give this one thing. I have literally been in the meeting in the room with the folks of the global ice community at JPL, and we've had this dialogue. And the problem is that if you get 1 foot, you're going to get 3. If you get 3, you're going to get 10, and so forth. And there's like 30 feet of low-lying ice around the world, and if we get 5 feet, we're going to probably get 35 or 40 feet. And that's just how that works because of all the low-lying terrestrial ice on coastlines all around the world. And I'll just leave it at that.
The thing is that that a lot of that ice is not in danger of moving. Yeah, if you go 4 meters, you're going to start moving a lot of that ice. If you get 2 meters, you probably won't. But anyway, if we raise sea level 4 meters, just take that as a nice number, nice round number. That is about 10% of the global population that will have to be displaced, including practically the entire population of the Netherlands, which is the densest country in Europe, made a significant country in Europe. And about 10% of the population in the US, including, of course, where Myron's sitting and where and Houston and the whole, and about half to 2/3 of the peninsula of Florida. So what happens when you try to move 10% of the population in a 5-year period? It doesn't go nicely.
That's why I'm selling my real estate in New Orleans and transferring to Colorado, maybe.
Yeah, we've had that conversation, Myron.
Right. Anyway, so
So that's my spiel.
Is there any silver lining?
I was going to do one last thing, and that was to look at a Gaussian curve, because basically everything, shall we say, moisture, temperature, and everything else that diffuses out from the center in a fairly normal Gaussian curve manner. And we think of the Gaussian curve in this nice, we all know what the normal curve looks like, except that really that normal curve should be looked at as an exponential curve. And if you look at it as an exponential curve, you get a real sense of what it really means to change the height of that curve. Move it up or down a little bit.
Paul, I don't know what you're saying.
This might be a good
curve
moment.
is a downward facing exponential parabola.
Yeah. Myron, I sent to you and the rest of the list a good graphic from NASA about what we've been talking about. It's a single image, and it might be useful food for discussion because it talks about Earth's energy budget, known in the Earth science community as ERBI, by the way, whatever. And but it talks about the incoming solar radiation and outgoing, and where all of the outgoing radiation is from, and how much is absorbed, and how much is by clouds, and how much is absorbed.
Wait a minute. Let me get the graphic on that. Did you, Brendan? Did you let me share the screen?
Yes, you have co-host. Yeah.
Yeah. Let me try. You're going to have to stop sharing, Paul, in order for me to share.
Stop. No, I don't want to do that one. I need to stop sharing. Stop share there. Okay, got it.
Let me try.
All yours.
Okay, there's.
Yeah, this is a NASA graphic. I'm sure Myron will get it up in just a moment.
He's got it up.
Great.
He's got it up.
It's a little old. It's a little old, but it hasn't changed very much. It's still pretty much exactly what we see there. And in Myron in particular is way faster at the math on giving percentages of stuff like this than I am. But we can look at the incoming solar radiation. By the way, this is all in watts per square meter. okay, and on the surface, right? So per square meter of what? Per square meter of the surface area. And
It's per
admittedly,
square
that
meter, it's per square meter perpendicular to the rays of the solar input.
And the standard number is 1,000, right?
no,
As
hold
you
on.
get to
I just want to clarify. Paul is correct. Right, because it's a sphere. And not only is it a sphere, you also have a very subtle, but not nothing difference at what altitude you're making the event occurring, you know, like where is the action happening. But mostly that's just noise. And however, Paul is correct because the Earth is a sphere. And as what he was saying is perpendicular to the rays of incoming solar radiance, it is what is meant by the watts per square meter. Okay, so as you move away from directly under the sun, that measurement changes a bit, right?
as the cosine of the angle of the latitude difference.
Right.
Yeah, right. And then, you know, time of year and all that. I mean, you know, blah, blah, blah. I mean, there's a lot to it, but just simplifying it down. Yeah, that's what we're talking about here. And when we look here about how much is reflected by reflected by clouds and atmosphere, you know, here it's 77 out of 340.4. And that's the total by clouds, just saying. And there's more from the surface. And my paper talks about albedo of the surface. And that would be reflected by the longer, lower second arrow, 22.9. And then we have all these other, look, there's a lot of complicated things. Emitted by clouds. Now, wait, emitted by clouds. That's different than reflected by clouds. That's talking about energy emitted by the surface that is absorbed into clouds and then radiated into space from the top of the clouds back out into space. Okay? So this is a complex diagram to understand. If you're just sitting here looking at it, all of this isn't necessarily obvious to you, right? That's why I'm calling out a few of these elements. Like, you know, this is the environment in which I did my research at Berkeley. All right, we were studying exactly this stuff. Just saying. And by the way, Paul, I want to say, we are both on the same side of this dialogue, and I would like to learn from you a little bit and update some of the stuff I'm doing based on what you're saying. Like, I would like you to read my paper and give me criticisms. You know, hey,
well, my problem with your paper was that you made the assumption that that this was a reasonable approach to take to actually cut down on solar incidence. And my problem is, I think that is absolutely not what you want to be doing.
I want to quote myself from this top of the second paragraph. It is the author's perception that this is a terrible idea.
Wait.
And then
okay, yes, you did say that. You did say
just
that.
a minute. Look, just a minute. I want to know, why am I looking at this graph? What is the key parts that tell me something new that I didn't know before? Okay, this picture on the screen that Richard just sent us in yellow, green, and red. What is the main point? What am I supposed to take away from this picture?
Well, I'll leave it to you, Paul, because you're our invited guest. You can, you know, I mean,
This is very similar. This is very similar. It presented a bit differently, but it's got very similar pieces to what I put in as a diagram early on that shows that about 23% of the incoming radiation is reflected by the clouds and aerosols, and about 9% is reflected by these off of the Earth's surface, and about uh, uh, and there's some absorption along the way, and then the Earth's surface is absorbing about 49%. Yeah, it's got just about the numbers. When you do the numbers on these, it comes out to be just about the same as what I had uh, as a diagram early on in
Yeah, but
my
assuming we
presentation.
understand all that, what's the takeaway?
The takeaway is that that if we change something in this balance, what is the effect? And that's what my question was: what is the effect on the people living on the surface and on the surface, and as
I
opposed
agree.
to
I totally agree. And,
Richard,
no,
let
hold
him
on,
talk.
hold on. I'm helping.
No, you're not.
Paul was really talking about that far right vertical of like it's an upward arrow made into chunks. Latent heat, change of state, creation of clouds, evaporation. That vertical column on the far right, 86.4, okay, is, again, that's just energy, but it's expressed in watts per square millimeter. And all I'm saying is that is exactly what the hell Paul was talking about, is that vertical, okay, which isn't part of the other set, right? And he's saying that the amount of energy available for that to occur is decreased, and the latent heat absorption is reduced, reducing cloud creation that eventually results in rain. Is that fair, Paul?
yes, and and the lack of rainfall is a major issue around the world.
All right,
Right.
And it hits, and unfortunately, what it really hits are the places that are less able to adapt to it.
I just want to let someone else talk, like I always do. I know Tor wants to say something because he always does.
Yeah.
I want someone else to chime in besides the two main speakers. Tor, you want to say something?
Um, um, I just noticed the net absorbed is 0.06 on this, 0.6. That number's doubled recently.
That's 6%.
Yeah, I mean the North Pacific this year was it was up in like 4 watts per square meter.
That's a great note. This dates from May 2010. Good point.
Yeah, because we've had a sharp increase since 2020, give or take.
Well,
Yeah.
in the North Pacific is also getting the atmosphere above it is getting cleaner as China cleans up its approach to energy production.
However, the dust from the Gobi Desert, the particulate matter and the nucleation of clouds, particularly over the North Pacific, was higher this year than it has in previous years.
Yes,
That's
because
the sulfate reduction.
the Gobi is being dried out by the lack of water coming in from the Indian Ocean around the west side of that, around the west side of the mountain chain of the Himalayas.
Well, it's
Agreed.
in part
And the Arctic.
higher wind energies, because we're
Right.
seeing over the oceans
Yeah.
and the ocean current acceleration. You're as you've warmed up the Earth, you've increased its energy, and the air is literally moving faster.
And we've reduced the amount coming down from the Arctic, just saying.
Reduce?
I mean, yeah, I think there's moisture reduction coming down to the Gobi from I mean, it's not huge, but it's non-zero, or it has been in the past. And
it's a rounding error. It's a rounding error.
I don't think so.
Moisture, there is so little evaporation off the Arctic that it can be almost ignored.
I agree.
You're talking about a
All
couple
right.
of orders of magnitude.
I'm talking about something a little bit different here. I'm talking about the transportation of the moisture, not necessarily the moisture source. The Arctic has been a source of significant winds that drive transport, and that has changed, is what I'm really trying to say. The winds are shifting, is another way to put it.
I might clarify that we're getting record amounts, 6 sigma amounts of moisture in both the Arctic and the Antarctic in the last couple of months of this year. Antarctica had a 3-week heat wave that blew out every record I've ever seen. The Arctic has had a 2 to 3 month heat wave with hitting 6 sigma moisture levels all over the place.
Wow.
Yeah, I mean it's running exactly what my geologic astrophysicist teachers taught would happen to the poles.
Yeah, I haven't had time to follow it. Thank you for doing so.
I want to ask a quick question. In a previous conversation with Paul Washington many hours ago, he said that we are having less hurricanes in New Orleans because of the dust being thrown up by the Sahara Desert. Does that have anything to do with what we're talking about just now?
It may. Again, you've got more wind shear. The ocean is warmer at a deeper level. It's warmer, so you've got more basic energy there. But the shearing force of the wind acceleration, you need kind of calm wind to form a hurricane.
There's another element here going on that is not well appreciated, which is what appears to be what many would think of as a reverse flow across the Atlantic from east to west. That is actually quite important. I'm not expert enough to articulate it all that well, but I do know that the dust from the Sahara, we're talking Sahara here, is actually really important to more to the Amazon than it is to us.
We've
but
been having dust falls in Texas this year from this Sahara.
May I share screen?
Yeah, I'll get off. You can handle it.
Yeah, I mean, real daily images off of Climate Reanalyzer, which is an excellent site hosted by the University of Maine. They collect a lot of satellite data and they publish it. They don't do really any analysis to it. Somebody needs to turn Jerry on.
I'm trying to turn it off.
It's up top of the screen.
Not on my screen, so I can get it on.
Well, somebody you need to stop sharing and
Yeah, at the bottom, Myron, if you pretend like you're going to share your screen, it's the same button to share, to stop sharing.
Well, I'm pressing it.
And what's happening?
It just tells me how you want to share it. Gives me the choice.
Let's see, who is sharing? Yeah, it's just sharing your screen. Let's see if I can cancel that. Stop participant sharing. There you go. All right,
You got
it to our. Well, yeah, I just stopped it. I just used
Okay.
options.
I'm in a meeting. This is the today's weather map of the centered on kind of North America that shows the 2-meter temperature anomaly in degrees Celsius. This is the remnants of the heat wave. If you look at it in standard deviation precipitable water, it's coming in. It's not as high as it was. It's in the 4 range. If you look at the precipitable water, you're getting moisture all over the Arctic in amounts that I've never seen before. But the key thing is the farther north you go, the crazier it gets.
Well, there is an interesting aspect to this that people don't generally talk about, and that is that the thickness of the atmosphere is fundamentally greater at the equator than it is at the poles by
Oh yeah.
significant. Well, as you add moisture in at the equator, it's getting even greater. And that causes a northward upper atmosphere flow that then comes down, is causing extra downward flow, in other words, high pressure downward flow in the of moisture air in the Arctic regions, and that'll push a lot of the winds.
Yeah, I agreed. You're looking at the here. This is the 500 millibar anomaly map, and it shows that this heat wave up here was an anomaly. Oh, that's what is that pushing for? And again, you dislocate all of the dry polar air in these blue areas. So
Mm-hmm.
this one just moved off the coast, but it was basically centered over Texas. Yeah, and so if you look at the precipitable water, what happens right now, this is the remnants of a tropical thrust that went up through the driest part of Arizona, Nevada, and Southern California, and that hit 6 sigma moisture levels. So you're seeing these where you're either extremely dry or extremely wet.
That is what our science predicted at Berkeley when I was there doing all that research, is that drier places are, I mean, let me rephrase this. It's going to mean where it's wetter and drier are going to shift and change, and that there would be a very chaotic period before it really totally settles out. This is like the high level single paragraph conclusion that we came up with. But it really fits what we're discussing now, 20 years later, roughly.
Okay,
Yeah,
listen,
exactly.
right now it's after 9 o'clock. I want to find a way to shut this down politely because we want to stick to an hour. So,
Yeah, I want to just show one other thing. This is the surface air temperature logs for the whole year, and this goes back. Oh, I think they go back to the 1950s. And I'm just going to go over Antarctica because this is what I've been tracking. This year, starting about here, you blew out every record of temperature. You can just sort of see along this line here. It's the darkest red line. It just jumped. Starting in August, it just went nuts. Now, I don't quite know geophysically what's happening between the poles and El Nino La Nina cycle, but again, when I just started seeing 30 degrees Celsius above normal over 2/3 of Antarctica with 6 sigma moisture levels, something's changed.
okay, I'd like Paul to have the last word, and then we'll shut it down.
Just going to raise one. I was going to raise one political question. Yes, we've got all these things going on, but we have changed the environment since the time of the onset of the Little Ice Age in the 1300s. We have put in hard borders all over the globe so that populations cannot move. This has been the problem with the migrants coming out of Syria, the Syrian civil war, which was partially driven by by climate change. It used to be that when we had a shift in where the rainfall was and where the dry places were and everything else that lasted more than people could deal with locally, they moved to where there was more rainfall. There was enough communication so that people in Central Asia, for instance, knew that the Middle East had food or thought they did. And that's when the Indo-Europeans moved down into the Fertile Crescent. That's what drove the groups out of Central Asia and into Europe. The Indo-Europeans again, but also there's a group before that did it. It's moved people around in North America. So what are we going to do this time? We've got hard borders. People are tied to their little piece of ground that is called a country. This is going to make real problems.
Welcome,
Already
well,
is. Yeah, you're right.
welcome
All
to
right,
the
thank
club.
you
You're
very
right.
much, Paul. Thank you very much. We are out of time. I hope this is educational for those who watched it. I certainly learned a lot. Thank you, Paul. Thank you, Richard. Thank you, Tor.